In this chapter, we have introduced several formulae without proving them, so now it's time to catch up with these proofs. It was introduced by the Italian mathematician Cavalieri in the 17th century. When you remember the argument about slant prisms, we used there a beer mat model, and actually this principle of Cavalieri is sort of a generalized beer mat model. The idea is the following: we have two solids, they have the same height, and their base face area is the same. We put them on the same base plane, and then we cut through both of the solids with a plane parallel to the base plane. And we'll look now at the intersection area that we get in both solids. And the principle of Cavalieri just says, if no matter at what height I place this parallel plane, and I look then at the cross sections, and the cross sections have the same area, then the volume of the two solids is the same. Applying the principle of Cavalieri to a slant or oblique, prism or cylinder, we see immediately that they have the same volume as the corresponding right prism or cylinder, since when we cut here at some altitude h, we will always get this base figure as a cross section, and in the case of a cylinder we'll always get the base radius, no matter where we cut. Now let us use this principle to prove the formula for pyramids and cones. In the first step, let us show that the volume of any two cones or pyramids that have the same height and the same base face area are equal. Let G be the base face area, H the height of the cone, and then x the height at which we cut through the cone or the pyramid. This cut generates a smaller cone, or here a smaller pyramid, so stretched versions of the original cone or original pyramid. The stretching factor from the larger cone or pyramid to the smaller one is obviously the height of the larger cone, so h divided by the height of the smaller cone, h minus x. And the cross-section area is then just k squared times the base face area, so h divided by h minus x squared times g. The same applies to the pyramid. The stretching factor is again h divided by h minus x, and hence the cross-section area is h divided by h minus x squared times g. So it is absolutely independent of the form of the base of this pyramid. We used here a square pyramid. We could have used any type of pyramid, and we see also it's exactly the same like the formula for the cross-section area of the cone. This means we have the same cross-section area at any height x, and this means, due to the principle of Cavalieri, that the two solids have the same volume. Arguing along the same lines, we can show that this holds also for oblique pyramids and cones. Now let us prove the formula for the volume of a pyramid or cone, which states that the volume is 1/3 times g, the base face area, times h, the height of the cone or pyramid. Let us look now at a prism with a triangular base. Here. We now split the prism in 3 pyramids as shown here. And now what we want to prove is that the volume of this pyramid is the same like the volume of this pyramid and like the volume of this pyramid. Since the 3 pyramids form together the prism, and since they all have the same volume, this means that each pyramid's volume is 1/3 of the prism's volume, so 1/3 times base times h. So let us now show that the first 2 pyramids have the same volume. The first pyramid has this base here and this height. The second pyramid is turned upside down, has this base and this height. Well, now comparing, we see they have both the same height, and the base face here and this base face are the same since they are the base and the top face of the prism. So the two pyramids have the same base face and the same height, so due to Cavalieri they have the same volume. Now let us show that the second and the third pyramid have the same volume. Now we'll look at this pyramid a little bit differently. We consider now this side to be the base face of the pyramid and this here to be its height, since we have a right angle here. For the third pyramid, we consider this to be its base face, and again here is its height. Here we have a right angle to the base. Well, this is just exactly half of this side face of the prism, and this here is the other half of the same side face, which means the two pyramids have the same base and the height is exactly the same, so they have the same height. So again we have shown they have the same base and the same height, their volume is the same. So this means that all the three pyramids have the same volume. The three volumes add up to the volume of the prism, so each of them has 1/3 of the volume of the prism, and we get the formula that we wanted to prove, 1/3 times g times h. The prism we chose in the beginning was an arbitrary prism with triangular base. So what we have shown is that for any pyramid with triangular base, it has this volume. Just before we showed that for any prism or cone with the same base face area, so independent of the figure of the base face, if it has the same base face area as the triangular based pyramid, well, and the same height as it will have the same volume. So the formula holds for any cone or pyramid. Archimedes is known to be the first person to have found the formula for the volume of a sphere. Here let us look at the proof provided by the German mathematician Johann Anders von Segner in the mid of the 18th century. We will compare the volume of a hemisphere with the volume of a cylinder into which a cone has been drilled and this part has been extracted from it. And we will show that these two volumes are the same. Both base faces are the same, namely circles with the radius r. We then cut through both solids at the same height x. The cross-section area we get when cutting with the hemisphere is a circle. To find its area, we have to find its radius r dash. R dash is perpendicular to x, and we know the length of this line here. It is the radius r of the semisphere, and hence we can find r dash using the Pythagoras. And we get that this cross-section area A1 is pi r dash squared, which equals to pi times r squared minus x squared. And expanding this, we get pi r squared minus pi x squared. The cross-section of this solid is an annulus, ein Kreisring. The radius of the outer circle is r, and the radius of the inner circle is x. The first one is obvious, the second one not immediately, so let's look at it more. Well, the height of the solid is just r again, because it's the same height as the hemisphere. Let us now look at a vertical cross-section through this solid, and we get this picture here. This part here is an isosceles right triangle, because we have the same length here, r and r. So this angle here is 45 degrees, which means that also this angle here is 45 degrees. And so this here is an isosceles right triangle, and hence this length is the same like this, so it is x. So the area of the annulus A2 can be calculated as the area of the outer circle minus the area of the inner circle, which is pi r squared minus pi x squared. And this is exactly the same as A1, the cross-section area with the hemisphere. So we have shown that the cross-section areas for any height x of the two volumes are equal, which means the volumes of the two solids are equal. Which means that the volume of the hemisphere is the volume of the cylinder minus the volume of the cone. The volume of the cylinder is pi r squared times r. The volume of the cone is 1/3 times pi r squared times r. So subtracting them from one another, we get 2/3 times pi r to the power of 3. And since the volume of the sphere is just double the volume of the hemisphere, we get finally that the volume of the sphere is 4/3 times pi times r to the power of 3, what we wanted to prove. We come to the last missing proof, the one for the surface of a sphere. Let us look as a preliminary reflection at an annulus. We can calculate its area exactly as the difference between the area of the larger and the inner circle, but let us instead find approximations using the circumference of the inner circle and the circumference of the outer circle, and we assume now that the width of this annulus is just d. This means it's the difference between the outer radius and the inner radius. If we cut the annulus apart here and then we sort of try to unfold it, so somehow to get that here, we'll get in the end something like a trapezoid, where this side here will be just the length of the inner circle circumference, and this side here will be the length of the outer circle circumference. The distance between the two lines is this width d, and note it will not really be a trapezoid because we really cannot unfold it, it's just symbolized in this way. However, what is true is that this area will be larger than this area, which means the area 2 pi r times d, and it will be smaller than this area here, which is 2 pi times the radius of the outer circle, so r plus d times d. So we found this inequality for the area of the annulus. Now let us find the surface of a sphere using the so-called soap bubble method. We put a soap bubble of thickness d around the sphere with radius r. Here we see the cross-section, so here is the original sphere. There is a soap bubble just around the sphere, and then we have r plus d is the radius of the soap bubble. Let us now find the volume of the soap. Well, it is calculated as the volume of the outer sphere minus the volume of the inner sphere. So 4/3 times pi times this radius r plus d to the power of 3 minus 4/3 times pi times this radius r to the power of 3. Now let us apply some algebraic transformations. First, let us factor out 4/3 pi. We get this expression here. Then let us expand this expression using the Pascal triangle. We get this here. Now the r to the power of 3 and the r to the power of 3 here cancel out. What remains is this. And last but not least, let us factor out d here, and we get this expression for the volume of the soap. Now let us use the same idea that we had in the beginning for approximating the area of an annulus to approximate the volume of the soap. So we use the surface of the inner sphere and we multiply it by the thickness d of the soap to approximate the volume. This means surface of the sphere with radius r times d is an approximation of the correct volume of the soap, but an approximation we know that it is too small. On the other hand, when using the surface of the outer sphere, this means the surface with the radius r plus d times the width of the soap times d, we get an approximation that is larger than the exact volume of the soap. Let us insert for the volume of the soap the formula that we found before. Next, we divide everything by d, and we get this inequality. Now let us look at what happens when we let the thickness of the soap become thinner and thinner. This means when we let d go towards 0. In this expression here, Since d goes towards 0, this expression will go towards 0, and the d squared as well. Remember, r is just a fixed number, so I have some number times d. d is becoming 0, so everything here goes towards 0. This means that the expression goes towards 4/3 pi times 3r squared plus 0, which is equal to 4 pi r squared. And the surface of the outer sphere, well, since it becomes closer and closer to the inner sphere, the surface becomes in the end the same like that of the inner sphere. And inserting these findings now in this inequality, we get, well, here we have SR. This, we said, simplifies to 4 pi r squared, and this is again SR. So we get this inequality here. And this means that the surface of the sphere is 4 pi r squared, what we wanted to prove.